All right, chapter 6 is our introduction to stoichiometry. Stoichiometry is something that when I was in high school, lots of students that took chemistry at my high school were like, oh, stoichiometry is the worst. It's so evil. I hate it. It's awful. And then when I got to taking chemistry here at Reedley College, I didn't see what all the fuss was about. But maybe that's a difference in teacher or something. Also, if you're hungry, my apologies. So our analogy to introduce stoichiometry is going to be BLTs, bacon, lettuce, and tomato sandwiches. The numerical relationship between chemical quantities in a balanced chemical reaction is what we call stoichiometry. It's basically how many of one thing versus another thing. That's really all it is. We're looking at primarily coefficients, so the numbers out in front of our chemical compounds. The reason that we like stoichiometry, knowing how things combine, knowing the products that are formed, is that we can make predictions about products that will form. Specifically, we can predict the amounts. So based on how much chemical we put into the reaction, we can use the coefficients in front of those to predict what we are going to get out of those chemical reactions as products. These calculations are central, integral, crucial, vital, important, other synonyms for those words to chemistry. That means we're going to use them all the time. This is going to become one of our new standard steps in our solution maps. We will do stoichiometry a lot, continuously, without ceasing. And I thought, what better way to introduce it than BLTs? And so I found these public domain images that had bacon, lettuce, tomatoes, and bread in them, and spent way too long clipping out a piece of bacon and lettuce and tomato and bread and then stacking them all up to make BLTs so that you have a visual. I didn't cook any bacon. I didn't eat any BLTs during this whole process. No animals were harmed in the making of these slides, at least on my part. So stoichiometry is basically a chemical recipe. A chemistry recipe is the idea. Or it's the ratio of our ingredients in a chemical recipe. So a recipe tells you how many ingredients you put in, and sometimes, hopefully, it'll also give you an estimate of the idea of how much you're going to get out. And this should not say pancakes. That was the old example. It should say BLTs, the number of BLTs that we're going to produce. Say we've got two friends, must be nice, and they're coming over and we're going to make BLTs. We want to know how many of each of these ingredients we need to get to be able to make BLTs for everyone. It would be kind of a shame if Justin and Ryan come over. Those are the names that came to mind. Justin and Ryan come over and they each want a BLT. Ooh, sorry, I've only got 2 slices of bread. Guess we're having open-faced BLTs, or we're just like all splitting thirds of a BLT. That sounds awful. So this helps us prepare the correct amount of product, or alternatively, it lets us know based on our ingredients that we have on hand how many we can make. We might make the executive decision to run over to Smart and Final or Save Mart if we're feeling like spending, and getting ourselves some more ingredients. So let's say that we have 4 slices of tomato, and for some reason we've just got tons of bacon, lettuce, lots of bread. We can make 2 BLTs, assuming we have enough of everything else. And we can figure that out. We can write out this relationship as a ratio. So looking at our tomato, takes 2 slices of tomato in this particular recipe, and that will go on to produce 1 BLT. So our relationship to tomato goes to 1 BLT. And there's, for a lot of these stoichiometry things, we're making an assumption. We're assuming that we have enough bread, we have enough lettuce, we have enough bacon. So if we've got 2 slices of tomato and everything else, we can make 1 BLT. So our starting amount, I don't know why I wrote it in red, 4 tomato slices. And if we put an equal sign instead of an arrow, looks an awful lot like a conversion factor. And that's how we're going to use it. So 1 BLT for every 2 slices of tomato. The tomato cancels out, and we get 2 BLTs out. So what we're doing in stoichiometry is we're converting the chemical, we're converting the ingredient instead of converting like the unit, like the moles or the atoms or the grams. So it's a new type of conversion that we've unlocked. Let's say that we have 8 slices of tomato. Assuming we have enough of everything else, how many BLTs can we make? So we're starting with 8 slices of tomato. Let's identify in our recipe our slices of tomato. And our goal here is to figure out number of BLTs. So we'll also identify our product. Our solution map is slices tomato to BLT. And our conversion factor for this problem is the coefficient with the tomatoes and the coefficient with the BLTs. Let's call it 2 slices of tomato, 2 ST equals 1 BLT. Since we're going from ST to BLT, we want the conversion factor form that has slices of tomato on the bottom. That's going to be the form 1 BLT over 2 slices of tomato. So our 8 slices, use our conversion factor, slices of tomato cancel, we're left with units of BLTs. What a tasty unit that is. And so we get that we can make 4 bacon, lettuce, tomato sandwiches. Questions about stoichiometry so far? In isolation, with real-world examples, I think it's not so scary. The way that we're going to be using this normally, though, is with a balanced chemical equation. This is actually our recipe. Not the stoichiometry. So this is our recipe. If we put in 3 hydrogen molecules and 1 nitrogen molecule, we'll get out 2 ammonia molecules, assuming the conditions are right. Got to set the mood. And so our equation shows us how we can combine these. If we put in 3 hydrogens and we have enough nitrogen, we can get out 2 ammonia. If we put in 1 nitrogen and we have enough hydrogen, we can get out 2 ammonia. If we've got 1 nitrogen, we can use that all up if we put in 3 hydrogen, and so on and so forth. So there's a bunch of different ratios that we can come up with. Let's say that we have 3 moles of N2 and more than enough H2. You'll often see and more than enough of the other things, or assume that you have plenty of the other things. That's just our way of covering our rears, so that you know that you can't just be like, well, you didn't say that you have any of that other thing, so you can't make any at all. That's the reason that it's there. You mostly don't have to worry about it. Okay, so we're starting with N2. Let's identify the nitrogen in our problem. The other thing that we care about, the thing we're going to, is ammonia. So we'll also underline the ammonia. Then we pluck those 2 chemicals and their coefficients and make our conversion factor. So we'll call that N2 equals 2NH3. Divide both sides by N2 to get our conversion factor, 2NH3 over 1 N2. You can also do it the other way. You can just flip it for free as well. So 3 moles of nitrogen gas times our conversion factor. The nitrogen cancels. The mole stays. Another way that you can do this is you can write, for our conversion factor, 2 moles NH3 over 1 mole N2. So you can pair moles with those as well and cancel those moles. So we get out 3 times 2 is 6. The moles pulls through, and our new chemical, NH3 ammonia. Our other question that we could ask here, or one other question, how many moles of nitrogen are needed to completely react with that amount of moles of H2? So what are we given in the second example? Yeah, we're given moles of H2. And we are looking for moles of N2. And of course, that should say needed instead of need. All right, so this time the 2 things that we care about, let's underline them in orange. Go Tigers. H2 and N2. So we'll pluck those out. Not 2, 1. So we've got a 3-to-1 ratio. I'll write in the moles this time. Since we're starting with moles of H2, we need to use the form of the conversion factor that will cancel out our moles of H2. So moles of H2 needs to be on the bottom. That looks like this. 1 mole N2 over 3 moles H2. When we do it this way, moles H2 cancels moles of H2. Our leftover units are moles of N2. That's what we want. So we probably have done it correctly. So MOL N2, and it'll be 2.3. Now I'll just use my calculator. My brain's fried. 2.3 something. 2.37, 6 repeating, so we'll call it 2.38 moles N2 after rounding. Questions about either of these examples? So this is our isolation work, looking at just the one step for stoichiometry. You will see probably a couple of these questions on the exam. More likely, we'll have some expanded versions where we add other steps onto the front and the back. That's what we're going to be doing for most of the class from here on out. But first, one for you to try. So water forms when hydrogen gas reacts explosively with oxygen gas, according to the balanced equation. How many moles of H2O result from the complete reaction of 24.6 moles of O2? Assume more than enough H2. An important step when picking apart word problems is identifying correctly the things that we care about and what the steps we need to do are. So we are starting with the one that's got the number, 24.6 moles of oxygen. That is our starting point. And the thing that we're looking for is moles of H2O. That's paired with our question words, how many? So we're looking for moles of H2O. It's right next to our question words. So even though the order is backwards, don't let that fool you. So the two things that we care about are the O2 and the H2O. So I'm underlining those in the balanced equation. We're going to pull those two out and make conversion factors from them. So our two options are 1 mole O2 over 2H2O, or the inverse, 2 moles H2O over 1 mole O2. Those are the two options. Since we're starting with 24.6 moles of oxygen, we need to pick the left or the right. Which one are we using? The left conversion factor form, the right conversion factor form? We're using the right one because it has moles of O2 down below, so that means we'll cancel out our moles of O2 that we started with. So what pulls through is moles of water and that should be 49.2 moles of water. Questions at all about that? All right, so as I mentioned earlier, we're also going to expand that out. So we're typically not going to be working with moles to moles directly, just because it's kind of hard to measure moles. Usually we're measuring the mass of reactants and the mass of products, because we can weigh those on a scale. So we've been doing this inside step, the moles to moles step. However, we've previously done mass to moles and moles to mass. The keys for those are, of course, molar mass. So this middle step is the new stuff. So rather than switching between mass and moles for the same chemical, A or B in this case, we can now switch from mass of A to the moles of A, use our stoichiometry to convert to a different chemical, and then find the mass of that chemical. Here's one that we can do for that. We've got a balanced equation given to us. How do I know that it's balanced? There's coefficients. Also, I'm the one that put it in there, so I know that I balanced it. So the quick trick, coefficients mean it's balanced.
This is a test of the State Center Community College First to Know notification system. This is only a test.
Thank you.
Attention Reedley Community College. This is a test of the State Center Community College First to Know notification system. This is only a test.
Thank you so much. Love that. All right. We want to know what mass of carbon dioxide. We have a question word, what, meaning that we are looking for mass of carbon dioxide, CO2. So looking for CO2, we underline CO2 in our problem. When 5 0.0 times 10 to the 2 grams of pure octane is burned. Octane is C8H18. So that's the other thing that we care about. We've got a little bit more information that we need to collect. We've got our middle step. We're starting with grams C8H18. What can we convert grams to? Moles. We can convert to moles of octane. What do we need to do that step? We need a molar mass. And from moles of octane, we can convert to what? Moles of CO2. Using our stoichs scoob. And from moles of CO2, we can get to mass or grams CO2. Again, using a molar mass value. So setting this up, have to go out and collect our molar masses and our stoichiometry ratio. Our molar mass for octane is 114.232 grams per mole. For CO2, it's 44.009 grams per mole. And if we're using our dimensional analysis, if we're looking at the units and letting the units guide us to our answer, that will inform us the way that we need to set up this calculation. So basically 500 grams of C8H18. We have grams. We need to get rid of grams to go to moles. So we're going to divide by our molar mass. That will cause our grams to get canceled out, our new units, moles of octane. Perfect. That's in line with our first stop on our journey. Then we need to apply our stoichiometry ratio. We have C8H18, so we need C8H18 to be on the bottom in our conversion factor for our ratio. So we'll be using that form. And this will cancel our chemical unit. So now we've got moles of CO2. I didn't see that. So we're now in moles of CO2. We apply our molar mass to get rid of our moles. So we're multiplying. And moles cancel. Our units that are left are CO2 and grams. So we'll multiply everything along the top. 500 times 16 times 44.009, divide by 114.232, and also divide by 2. You can do those in any order. It doesn't matter. You can do them left to right, top then bottom. And our answer is 1,541.039 ... grams CO2. Because our starting number had only 2 significant figures, we are only going to have 2 significant figures in our answer. So 1.5 times 10 to the 3 grams of CO2. Any questions about that before I turn you loose on your own mass-to-mass stoichiometry problem? All right, your turn to have fun. What mass of octane would be needed to generate 42.3 grams of water? Again, try not to get confused by the way the question's phrased. Identify what you're given, identify what you're finding, and let the units guide you. To save you from the step of coming up with the molar masses, I'm just providing you with all of them. Okay, so the thing that we are given is the one with the number, 42.3 grams of water. Let's underline water in our problem. That's our H2O. And we are looking for a mass of octane, octane being the C8H18. Starting with our 42.3 grams H2O, we need to first convert to moles before we can use our stoichiometry. So we're going to divide by our molar mass. That'll get our grams to cancel. We are now in moles of H2O. It is at this point that we can use our stoichiometry. So we'll produce 18 moles of H2O for every 2 octane that we put in or burn. So our H2O and moles cancel, and I forgot to put in another moles. So our unit now is moles of octane. We're looking for a mass, so that means we need to multiply by our molar mass. So 114.232 grams over moles. The moles cancel. Our output here is grams octane. And I just typed everything in a way that it wouldn't work, so we'll do that again. I got 29.8, we'll leave it at 3 sig figs, grams of octane. Any questions about stoichiometry? That'll do it for class today, and on Thursday we'll get back to bacon.